Statistics Lessons 4.4 Counting. Develop the ability to apply the fundamental counting rule, factorial rule, permutations rule, and combinations rule. Distinguish between circumstances requiring the permutation rule and those requiring the combination rule. So the first rule, multiplication counting rule, for a sequence of events in which the first event can occur n sub 1, the second event can occur n sub 2 ways, the third event can occur n sub 3 ways, and so on and on. The total number of outcomes is n sub 1 times n sub 2 times n sub 3. Now, let's see. What does that actually mean? Let's see here. What about 4-digit passcodes? You got a 4-digit passcode. 1, 2, 3, 4. 4-digit passcodes. How many digits can this first passcode be? Well, how many digits are there? Single digits. 0, 1, 2, 3, and so on, and 9. So there's actually 10. So the total number for the first one is 10. The second one is 10. The third one is 10. And the fourth one is 10. So using the multiplication counting rule, that would be 10 times 10 times 10 times 10. And that is 10,000. All right. I wonder what the probability of guessing the correct passcode on the first attempt would be. Well, if you were to guess it on the first one, that would be 1 over 10,000. 1 out of 10,000. Or 0.0001. Not much of a chance, is it? Factorial rule. The number of different arrangements, order matters, of n different items when all n of them are selected as n factorial. Okay. Now what would be a good example of that? So let's see here. Let's see here. A statistics researcher must personally visit the presidents of, we'll say, Gallup and Nielsen and Harris, Pew, and Zogby. Okay, so how many total are there? There's 1, 2, 3, 4, 5. So how many choices for his first trip? 5. How many choices for his second trip? 4. How many choices are left for his third? 3. How many choices for his second? And then his first. So 5 factorial would be 5 times 4 times 3 times 2 times 1, 20, 60, 100, 120. 120 ways you could go visit those 5 presidents. 120 different ways. Pretty cool, huh? When using different counting methods, it is essential to know whether different arrangements of the same items are counted once or are counted separately. That's how we distinguish between permutations and combinations. Permutations of items or arrangements in which different sequences of the same items are counted separately. Okay? Example. How about ABC? How many different ways can you do ABC? A, B, well, let's do it like this. Let's do it like this. How about A, B, C, or it could be A, C, B. It could be B, A, C. It could be B, C, A. It could be C, A, B. or CBA. So that's 1, 2, 3, 4, 5, 6. There are 6 ways that you can do this. All right. Now let me show you something else in your calculator. If you want to calculate permutations, menu, and then 5, 2, and it would be 3, A, B, and C, 3 to 1. I'm sorry, menu, 5, 2, it would be 3, comma, 3, and that gives you 6, okay? And that's what we found, 6. So that's permutations. So that's menu, 5, 2 in your calculator. Combinations of items are arrangements in which different sequences of the same items are counted as being the same. Well, we used the letters A, B, and C, right? How many? There's maybe 6 different ways, but really we only used A, B, and C, so that would be 1, okay? And if we would try that in our calculator, menu, 5, 3, and that would be 3, comma, 3, and that gives you 1, okay? So that's menu, 5, 3. All right, now we're still kind of vague. Let's see if we can expand on that. The permutations rule. When all of the items are different, when n different items are available and r of them are selected without replacement, the number of different permutations or order count is given by NPR, which is n factorial divided by n minus r factorial. And to use what we did before, we had 3 factorial, and this was the ABC problem. ABC problem, 3 factorial, and then that would be 3 minus 3 factorial. So we have 3 times 2 times 1 over, and 3 minus 3 would be 1, and that leaves you with 6, okay? Now, let's try a different example. In a horse race, a trifecta bet is won by correctly selecting the horses that finish first, second, and third. You must select them in order or in the correct order. The 140th running of the Kentucky Derby had a field of 19 horses. How many different trifecta bets are possible? All right, so we'll try the formula, and we're going to have 19 P3, and that's going to be 19 factorial over, and that's going to be 19 minus 3 factorial. Okay, so let's try that one. Let's see. Control divide 19 factorial, and that's going to be menu 5, 1 over 19 minus 3, and then menu 5, 1, and that gives you 5,814. Well, we could just use the menu 5 to the permutations, and we go 19, comma 3, and that gives you 5,814. All right. So, 5,814. Factorial is menu 5, 1. All right. So there are 5,814 different possible arrangements of those 3 horses. And I guess if you were laying a bet, it would be 1 out of 5,814. Okay. Permutations rule. When some items are identical to others, the number of different permutations order counts when n items are available and all n of them are selected without replacement. But some of the items are identical to others as follows. That would be n factorial divided by n sub 1 factorial times n sub 2 factorial, and yada, 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 n sub k factorial, where n sub 1 are alike, n sub 2 are alike, and so on, and n sub k are alike. Now that sounds a little bit, let me give you an example to kind of help you with that. When designing surveys, pollsters sometimes repeat a question to see if a subject is thoughtlessly providing answers just to finish quickly. For one particular survey with 10 questions, 2 of the questions are identical and 3 other questions are also identical. For this survey, how many different arrangements are possible? Well, we would say 10 factorial divided by 2 factorial times 3 factorial, which would be 10 times 9 times, well, let's just do it in the calculator. That'd be easier. So we have control divide 10 menu 5 1 over 2 menu 5 1 times 3 menu 5 1, and that gives you 302,400. 302,400. So there are 302,400 different possible arrangements for 10 questions. That's a lot, isn't it? Now, would you actually use all of them? Probably not. How many people do they usually survey? When they do that, it's usually around 1,000. Okay, it's usually around 1,000. So it probably wouldn't use all of them. Combinations rules. When n different items are available, but only r of them are selected without replacement, the number of different combinations is found as follows. NCR. In California's Fantasy 5 lottery game, winning the jackpot requires you to select 5 different numbers from 1 to 39, and the same 5 numbers must be drawn in the lottery. The winning numbers can be drawn in any order, so order does not make a difference. How many different lottery tickets are possible? Find the probability of winning the jackpot when one ticket is purchased. So let's try that. Let's try it. Let's answer the first question here. Let's answer the first question. How many different lottery tickets are possible? Okay. Order does not matter. So we can use the combination thing. So what do we got here? We got 39 choose 5. And that's going to be 39 factorial divided by 39 minus 5 factorial times 5 factorial. Okay. And let's see, that's going to be 39 factorial over, and that would be 34 factorial times 5 factorial. And let's just use a calculator. Control divide 39 menu 5 1 over 34 menu 5 1 times 5 menu 5 1. And that comes out to 575,757. Well, that's different, isn't it? All right. Well, is there another way to do it? You could use menu 5-3. Menu 5-3, and we have 39, comma 5, and we get the same answer. Okay? That's menu 5-3. The second question, find the probability of winning the jackpot when one ticket is purchased. So that would be 1 over 575, 757. Okay? Not a real big chance, is there? Not a big chance there. Think about it. Well, anyway. Permutations or combinations. How do you know when to use which one? How do you know when to use which one? Example. The Google company must appoint 3 corporate officers, a chief executive officer, an executive chairperson, and a chief operating officer. It must also appoint a planning committee with 3 different members. There are 8 qualified candidates, and officers can also serve on the planning committee. Okay, so let's see here. We got 3 corporate officers. All right. Now, let me ask you. CEO is the big dog. That's number 1. Okay. Chief operating officer is usually number 2. And the executive chairperson is usually number 3. Okay. Or some it's 1, 2, and 3. Either way. At Google, I think it's 1, 2, and 3. So it matters. Okay. Your pay is, if you're CEO, your pay is more than the executive chairperson. If you're executive chairperson, it's more than the chief operating officer. So it matters whether you're the CEO, the executive chairperson, or the chief operating officer. It really matters. So that's a permutation, and we'll do AP3. Okay, let's try that in our calculator. Menu 5, 2, 8, comma 3, and that's 336 ways. Okay, 336 ways. 336 ways. Now, how many different ways? All right. How many different ways can the committee be? Now, does it have a hierarchy on the planning committee? Okay, it does not. Okay, it does not. So as long as you're on the planning committee, so that one is going to be 8P or 8C3. 8 choose 3. So let's try that. Menu 5, 3, 8, comma 3, and there's 56 ways. So there's 56 ways those 3 could be chosen. With order taken into account, there are 336 ways. 336 ways these first 3 can be chosen. All right. Big difference. Big difference. And we'll work on this more in class. Y'all were great. I will see y'all in class tomorrow, and have a wonderful evening.